For RCR TV, I'm Sean Kinney, and welcome to HetNet Happenings, where we take a look at all things DAS, Wi-Fi, small cell, and much more.
Thank God that's over.
Woo.
CommScope, thinking beyond today's technology to help you make the best decision for your network and your business. Register today for the Wireless Infrastructure Show, the premier national event for mobile network solutions, produced for the industry, by the industry. Telecom Careers, the #1 global telecom and wireless job board, telecomcareers.com.
Welcome back to HetNet Happenings. The folks in the production booth tell me that you caught a glimpse of Chris and I's warm-up exercise there before the ad unit, so a rare peek behind the scenes.
Yeah,
you're welcome.
It's the way we sort of celebrate. When Sean gets that opener right, we just kind of like to sort of celebrate it.
So HetNet Happenings. This is my executive producer, Chris Martin. First time, long time, I believe, right?
That's right.
Well, welcome to the show. We appreciate you joining us, and I look forward to really tapping your deep knowledge of the wireless telecom industry.
It's
going to be a short show, isn't it?
Good luck.
Yeah,
good
all
luck.
right.
It won't be a very long show.
All right, well, first
I'm sort of one of those mile wide and inch deep kind of guys.
Gotcha. Depth, but very shallow depth.
Right.
All right, well, first up today, we're going to talk a little bit about small cells. This is a recurring topic on this show. It's even right there in the tagline. And, small cells are going to figure significantly into 5G cellular standards. Right now we have 4G LTE, right? That's the thing. But they're always working on the next big thing, which is going to be 5G. A lot of the markers of 5G, spectral efficiency, accessing new higher frequency spectrum, and then super dense urban networks. That's where small cells come in. They're exactly like what they sound like. They're tiny little base stations that provide coverage and capacity in a narrow geographic area, and they work because they're hooked up to the big cell tower that you're familiar with. So my colleague Martha DeGrasse had the opportunity to sit down with the gentleman from National Instruments, and they talked a little bit about how small cells are going to figure into 5G networks. Let's sit in on that interview.
Welcome back. We are here with Jeff Phillips. He is Senior Product Manager for LabVIEW at National Instruments. Jeff, we've been talking about your research around 5G, and I wanted to ask you specifically about small cells. We've heard for several years now that small cells were just about to take off, and it really hasn't happened as many people predicted yet. What are you seeing in your research that might actually change the trajectory for small cells?
Of course, yes. As you mentioned, small cells have been the front runner in 5G research for the last few years. And I think as you look at the emergence of massive MIMO and millimeter wave as complementary technologies, I really think that the development of those, the theories behind those will help small cell get to the point where a lot of the pundits were expecting it to be, frankly, by this point already. The higher frequencies that we're seeing at a millimeter wave will help with the application of densification within the small cell research area. And I think that combining the theories behind millimeter wave and packing together a higher frequency and at some of the more exotic frequencies like 73 gigahertz will really enable the application of small cell in a higher frequency range where you can really start to take advantage of the theoretical advantages behind small cell and densification.
Okay, great. And you did mention 73 gigahertz and the exotic frequencies. You know, I've heard 30, I've heard 60, but you've probably got a good line on it. What are some of the frequencies that we're going to see?
Yeah, so the Nokia Network's working example is the 73 gigahertz link, and that's the fastest working link that we've seen. We've seen some in frequencies like 28 gigahertz and 38 gigahertz, and some at 60. Those are the four kind of primary gigahertz ranges that I've seen functionally. 73 is by far the largest band that we've seen a functional link working in.
Now, how did these get identified? Just trial and error, try each one? Or?
Yeah, I mean, honestly, above the 6 gigahertz range, a lot of that frequency band is largely unclaimed, which is where a lot of the excitement behind millimeter wave comes from, is because there's just so much more bandwidth available that a lot of the research initially going into 5G were, how do we get more bandwidth through just the 6 gigahertz, the under 6 gigahertz frequency ranges? And when you look at the Shannon theory, you know, we're already kind of at the edges of signal to noise ratio with a lot of the advanced signal processing techniques. And when you've maxed out signal to noise ratio, your only other option is to increase your bandwidth. And so going above 6 gigahertz and even into the 28s and the 38s give you just such a wider range of frequency spectrums. And now some of the more advanced signal processing techniques and using high gain and phased arrays give you the advantage to take care of some of the loss, the high loss that you typically would have seen in those frequency spectrums.
Well, it is exciting.
It's
Jeff
very
Phillips,
exciting.
Senior Product Manager for LabVIEW at National Instruments. Thanks again for coming into the studio today.
Of course, thank you.
That was our editor, Martha DeGrasse, speaking with a representative from National Instruments about how small cells figure into 5G. And mentioned earlier, 5G is something we talk a lot about here on HetNet Happenings. And any of the viewers want to learn about that a little bit more, we've had some great interviews in the past with Robert Heath and Jeff Andrews from the University of Texas Wireless Communication and Networking Group, These guys are really on the leading edge of that 5G research, and there's some really insightful commentary if you want to check out our archived HetNet Happenings.
So, Sean, it occurs to me that I'm not like a top-level nerd, but I do appreciate...
Don't sell yourself short.
No, but I do self-identify as a nerd, but I certainly don't know as much as, you know, our guest that Martha interviewed. But I'm a nerd enough to know that I really get sort of chapped when I'm walking around and I can't get good service. And I'm in the middle of a city somewhere. So is the ultimate goal to make it so that all of my frustrations with that are going to fall by the wayside?
That's right. That's your heterogeneous network. You're able to move seamlessly from an in-building Wi-Fi connection outdoors to the small cell and then into a big stadium with 70,000 other people. You're connected to the distributed antenna system, and you always sort of maintain that robust wireless experience. That's the whole point of it.
So I won't have to worry about my Pandora song that I'm in the middle of when I walk out of my building being truncated.
No, you'll be able to do all of your important texting and internet research seamlessly from anywhere. Someday, we hope.
That's Buck Rogers time.
Yeah, well, it's something to look forward to. You know, Chris, earlier in the week, Chris hosted Angry Dad Gamer, which is a Twitch TV stream that we streamed live from the RCR ATX Studio Lounge. And I'll tell you, the most insightful part of the program, I thought, was from your son Grant making his commentary about the Halo Master Chief Edition there.
Yeah, Graham and I started playing Halo recently, and to be hanging out with, he's 11, so to be hanging out with a couple of big guys who really know how to play the game and so on, he was pretty geeked and excited about the whole thing.
Well, I mean, his smack talk prowess is up there with the best. I think I learned some new words, and I thought I had a pretty deep bench of swear words.
Yes, we did have a little bit of a father-son conversation about a few of the smack talk words. That
you encouraged it, right? You're like, hey, that was a good one, but maybe if you hit the first syllable a little harder, it'll drive it home.
I was a little uncomfortable as a dad, but CK Sample from Chaotic Moon did also appreciate it and complimented him on it. So
I enjoyed it.
I guess that it's hard to when a real life tech powerhouse like CK Sample applauds your smack talk.
Yeah, you're onto something.
Yeah, and it certainly makes any discipline on my part sort of
tough
a
sell.
little blunt. Yeah, a little blunt.
Well, we talked a little bit about small cell, and now we're going to do something we've never done on HetNet Happenings before. We're actually going to look into the fiber optic cabling that makes all this stuff work. That's the small cell that's downtown is, sometimes there's radio backhaul, sometimes there's microwave backhaul, but in a best case scenario, that thing has a line of fiber connecting it right to the base station. And fiber, it might sound like a dull topic, cabling, but it really is what transmits all the data.
It's incredible. It's really, when you talk about fiber optics, it really is that what you're talking about there is, although it's been around for a long time, it really is. That's Buck Rogers time. I mean, that you're sending signals through a wire made of glass. That's, to me, that really, I geek out over that kind of stuff. That's pretty real.
You're going to love this next clip. We had the opportunity to talk with the folks from CommScope. We spoke with one of their engineering fellows, Paul Colasar.
Down in CommScope, I mean, they're eating fiber optics for breakfast.
Oh,
They
yeah.
live,
I mean,
eat,
DAS,
breathe.
all that stuff. They got their hand in a lot, and they're doing some really forward-leaning research. They had a really big demo a couple weeks ago out in LA, but let's let Paul Colasar tell you about it. If we could roll that clip, please.
Today, we have a couple of grades of what's called laser optimized multimode fiber available, commonly referred to as OM3 and OM4. These fibers are optimized to maximize the capacity at a single wavelength, which is 850 nanometers, otherwise known as short wavelength. Most, if not all of the major applications today run at 850 nanometers because they take advantage of this window in the fiber, the spectral window, to get the most out of it. The OM3 fiber provides us with 2,000 megahertz kilometer of bandwidth, and we were able to transmit about 300 meters at with the OM4 fiber, it offers more than double that bandwidth, 4,700 megahertz, and IEEE has rated the transmission distance on that to 400 meters, or 10 gigabits per second.
Okay, so you mentioned, I'm sorry, go ahead.
So that's what we can do today with the fibers of today. And they will transmit greater capacity than 10 gigabits by going parallel. That is using multiple fibers in each direction, and each one will carry 10 gigabits or even more than that at 25 gigabits per second. So we can transmit 40 gig or 100 gig in the parallel fashion as something known as parallel transmission. The new fiber is designed to help us reduce the number of strands of glass in each direction by using a different multiplexing technique called wavelength division multiplexing. Now, this is a technique that's been commonly used for decades in long-haul transmission over single-mode fiber. And in that case, we're using single-mode lasers operating at 1,300 nanometers or 1,550 nanometers, in that range, to go and multiply the capacity of the fiber. We're going to do the same thing with multimode fiber, only this time we're going to use short wavelength division multiplexing, which means we'll be able to continue to use the low-cost sources which were fundamental in delivering the cost advantage of multimode transmission at 850 nanometers by adding a different set of wavelengths at slightly longer values, longer wavelengths than 850. So we'll be having, for example, 4 wavelengths fit into a 100 nanometer spectrum. So for example, 850 nanometer transmission plus 880 nanometer transmission, plus 910 nanometer transmission, plus 940 nanometer transmission. Putting all 4 of them together means we can get 4 times the capacity or reduce the number of strands in each direction by a factor of 4. And so we have now 2 multiplexing dimensions to take advantage of. We'll have the traditional space division multiplexing with multiple fibers, and onto that we will add multiple wavelengths and increase the capacity by a factor of 4. So for example, what that will do for us, it'll allow us to take what IEEE has just standardized, the second generation of 100 gigabit Ethernet, which operates at 25 gigabits per second on each of 4 fibers. So 4 times 25 being 100 gig. We'll be able to collapse that down to a single strand of glass with 4 wavelengths. And we'll be able to take that forward to say 400 gigabits per second. And instead of using 16 fibers, be able to use only 4 fibers. So you can see we're getting a much higher efficiency out of each strand of glass and be able to bring the cost of the cabling down that way.
Okay, and you mentioned the IEEE standard that applies to what we're talking about. Can you sort of take us through the research and development that went into coming up with the transmission scheme and then taking that into a standardization?
Yes, I'd be happy to. We started working with some transceiver partners and fiber manufacturing partners a couple of years ago making, having discussions on what kind of solutions would benefit both them and us. And what we found was a great confluence in going with wavelength multiplexing. And we knew that we could add additional capacity by adjusting the bandwidth characteristics of the fiber to allow for a broader range of wavelengths to be supported. And the transceiver companies were also indicating that they were moving in that direction. So last October, we brought our partners together into the TIA, TR42, into a subcommittee that I chair on optical systems, and made a proposal to begin a new project to standardize a fiber that could have this type of bandwidth characterization and therefore support this sort of multiplexing at for future IEEE and fiber channel applications. And I think, as I mentioned already, 100 gig Ethernet certainly an application that we could leverage this to its advantage. We could also apply this to a second generation of the newly drafted 128 gig fiber channel. That is similarly using 4 lanes of fiber in each direction. We could collapse those down to 1 strand as well. And this would get folks back to the 2 fiber paradigm that they've been used to all the way up through 16 gig and now 25 gigabit. They'll be able to extend that to 100 gigabit and get another generation out of that 2 fiber interface that is so popular.
Yes, so if I'm understanding correctly, you can really put the efficiency of the transmission, and that's where you derive the major increase in the throughput speed?
Correct. You add another wavelength, you essentially double the capacity. So each wavelength carrying the same amount of information as the previous one just multiplies the capacity of the fiber by that much. And by the way, you wanted to know about what we did at OFC. This last month, there was a big show, a big trade show out in California, probably the biggest optical show on the planet every year is OFC. And we partnered with Finisar, a leading transceiver vendor, to demonstrate their what they call short wavelength division multiplexing transceivers. They have designed transceivers at 40 gigabits per second with 4 wavelengths and at 100 gigabits per second with 4 wavelengths. So both of these are able to operate on 2 fibers, 1 in each direction. They demonstrated their capability on OM4 fiber as well as on wideband fiber. On the OM4 fiber, they were able to transmit 100 meters, and on the wideband fiber, 225 meters, which tells you that the increased bandwidth of the wideband fiber has come into play by extending the reach. It will similarly extend the bit rate as kind of a trade-off, reach versus bit rate, and it can also extend the application space for the shortwave division multiplexing. So shortwave division multiplexing is a sort of the cornerstone technology for the transceivers, and the wideband fiber, the wideband technology is the cornerstone technology for the fiber. You put them both together and you get an enhanced transmission system.
Okay, and so if you can help put this into sort of a practical context for us, if I am operating a data center and am able to adopt this technology, what benefits am I going to see?
Well, you will immediately be able to see a reduction in the number of strands that have to be deployed to support these high bit rate applications. You'll, for example, be able to reduce your strand count from 4 in each direction to 1 in each direction at 100 gigabits. And for example, at 400 gigabits, which is now being standardized by IEEE, instead of 16 strands in each direction, each operating at 25 gig, you'll be able to collapse that down to 4 strands in each direction with 4 fibers, each carrying 100 gigabits apiece. And if we increase the lane rate to 50 gigabits per second, then we'll get a further reduction in the number of strands or the number of lasers on the same number of strands. All of this works in concert to reduce the cost of the total system on the cabling because you're needing fewer strands of glass, and on the transceiver by making it more efficient as you move up into the data rate, higher data rates. You need fewer lasers.
Okay, and you mentioned the demonstration last month out in California. Is the technology going to be made market ready here in the short term?
Well, that's a good question. Yes, two things. Finisar's announcement at OFC was to say that they were going to bring out a 40 gigabit shortwave division multiplexing transceiver, which will operate at 10 gigabits per lane on each of 4 colors, the 4 shortwave color wavelengths I mentioned before. And it will operate on OM3 and OM4 and wideband. And of course, you will be able to go further and further distance on each of those 3 different types of fiber. CommScope is also planning to release a product within this year. I believe it's targeting the 3rd quarter. And it will be a wideband product such as we demonstrated with Finisar. It will look it'll look and terminate like traditional fiber. It won't be visibly different other than perhaps the sheath color. So it will be distinguishable from OM3 and OM4 because of this new property. And that you'll be able to immediately tell if you've got this wideband fiber in that you can now do these extended reach or extended bit rate application support over your cabling. So yes, we will see both transceivers as well as new cabling products come out within this year, both going in this direction of supporting shortwave division multiplexing on wideband fiber.
That was Paul Colasar. He's an engineering fellow at CommScope, and that was also me interviewing Paul Colasar,
Oh, really?
engineering fellow.
Excellent job, Sean.
You may be asking yourself at home, well, wait, you're wearing different clothing, and in that clip you were seated at a table. Don't worry, that's just the magic of television.
It's amazing.
We do that all day long.
That's right. It's editing.
All right. Well, Chris, I want to put in a plug here. Our viewers will notice one of our sponsors, PCIA, the Wireless Infrastructure Show. That's coming up April 27th to 30th at the beautiful Westin Diplomat in sunny Hollywood, Florida, my old stomping grounds.
All right.
I put in the plug because I will be hosting a panel there this year. We'll be talking about backhaul, the spine of the network. We've got some great guests from Clearfield Wireless, from Expo, and from DragonWave. Should be a lively discussion.
You'll find Sean there when he's not by the pool.
That's right, by the sunny pool at the Westin Diplomat in beautiful Hollywood, Florida.
For sure.
I really like it down there, though. I moved to Austin from Key West, Florida, and spent some time in the Miami Lauderdale area before that, and it truly is a lawless swamp. I really thrived.
Very nice.
Yes.
You're talking about Austin, right?
No, Florida.
Oh.
It's also it's hot here, and we have the humidity, but the mosquitoes, a little better.
Better here?
Yep.
Good. Well, that's good.
All right. Well, Chris, I want to thank you for joining us on this episode of HetNet Happenings. I want to thank our editor, Martha DeGrasse, our guest from National Instruments, and, of course, Paul Colasar from CommScope. For a lot more telecommunications news and multimedia content, you can visit rcrwireless.com. You can check out the RCR TV page. You can also visit our YouTube channel.
You said plage.
Plage? Pardon me. We'll have to run through the script earlier. That's, the best in the business. Chris Martin, ladies and gentlemen. Thanks for tuning in to HetNet Happenings. We'll see you next week.
HetNet Happenings is a production of RCR TV. To reach Sean Kinney or to suggest a show topic for HetNet Happenings, you can reach Sean at skinney@rcrwireless.com. On Twitter at SeanKinneyRCR. To find out more about the latest in HetNet and all things wireless, dig into rcrwireless.com.